Okay, so we will continue with the lecture. We were in part 4, which was quick review of matrices and vectors. Okay, in the last two videos, we have seen the review about the matrices, and in this video and the next one, we will see the review about vectors. Okay, so this is quick review about matrices and vectors. Okay, so part A was about matrices, and in this section A was about matrices. In this section B, is going to be about vectors. Okay, and so let's do some definitions. Okay. Definitions. The first one says a column vector. Let's define some important concept. Column vector often sometimes just called a vector, often just called a vector, okay, is a matrix with a single column. A single column. Number 2, a matrix with a single row is known as a row vector. Okay, so a matrix with a single column is known as a column vector, or simply called a vector, and a matrix with a single row is just called a row vector. Okay, we don't call it a vector, we call it a row vector, but when it is a column vector, we can just say a vector. Okay, so let me write this down. A matrix with a single row is a row vector. A row vector. Okay. The entries of a vector are known as component. Compared to when we study the matrices, we have seen that its elements are known as entries, but when it comes to vectors, the elements of vectors are known as components. Okay, so the entries of a vector are known as component. A column or row vector whose components are all zeros is known as a zero vector. So whether it's a column vector or a row vector is just known as a zero vector. Okay, so column or row vector whose components are all zeros is a zero vector. Is a zero vector. Okay. Okay, so let me give a small note here. Okay. It's a not it's N, not H. Okay. Note a vector is denoted compared to a matrix. A vector is denoted, okay, by a lowercase Roman letter or even Greek letters, okay, overlined with an arrow, or sometimes people use a bold face. Okay, so, but in this lecture, in this in yeah, in this module, we are going to use arrow instead of bold face. Okay, so a vector, I say a vector is denoted by lowercase case Roman letter, Roman, even Greek letters, okay, overlined with an arrow, overlined with an arrow. Okay, so we have something like A or alpha, okay, with the arrow on top of it, or sometimes bold face is also often used. Okay, is also often used. Okay, they are useful in books. Okay, so that means on papers, but not when you are writing it on a board. So you should write something like that. You see, it's not practical. So we are going to use the first option. So I'm going to say, so bold the A as no arrow. So it's just going to be bold A. Bold face alpha. See, it's not. It is taking too much time, so we won't use that second option. So let me give you an example. We have a vector V whose component, that means its entries, are 1, 2, minus 3, 0. Okay, and so another note here, a 0 vector is just denoted by 0. Okay, a 0 vector is written as 0, just like that. Okay, let's continue with another definition. Okay, so the linear system, okay, with okay, let me write it down. The following linear system, linear equation, the linear equation written as a1 x1 plus a2 x2 plus dot 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 an xn equals to d with unknowns x1 x2 xn is let me change colors. This word is important, is satisfied if you remember the first part of this chapter, we have defined when a set of elements, that means n tuples, satisfy a solution, an equation, sorry, when an n tuple satisfies an equation. So we are going to do the same thing here for vectors as well, okay? Satisfied, okay? That equation is satisfied by the following vector, S. Okay, so that's a small s, okay. Okay, my small x looks like capital S, but it's small s. Maybe I should say something like this. Okay. Satisfies S1, S2. Okay. Satisfies S1, S2, Sn. Okay. If we can substitute in the equation the s's for the x's. Okay, if a1 s1 plus a2 s2 plus dot 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 an sn equals to d. Okay. Okay, so that's the first definition. I should actually say definitions. That's the first concept we have defined. Okay, we are going to apply the same concept for a system of equations. Okay, so a vector satisfies a linear system of equations if it satisfies each equation in the system. Okay. Okay, so let me go to the next page and continue with number 3. We have a vector addition and scalar multiplication is very important for us to write the final form of a solution set. Okay. Vector addition or vectors addition, it doesn't matter. Okay, vector addition. Okay, the vector sum of u and v is the vector of the sums of the sums is the vector of the sums. Okay, that means let's say we have u, let's say u equals, okay, so let me do u. Okay, yeah, I'm going to expand it just a little bit. Okay, so let's say we have a vector u whose components are u1, u2, un. Okay, and v components, whose components are v1, v2, vn. So w, let's say we are asked to find the sum. Let's say w, the new vector w is u plus v. So how would we do the addition of two vectors. First of all, they must have the same dimensions. That means that they must have the same number of elements. They must have the same number of components, okay? So we have u1, u2, un plus v1, v2, vn, which is going to be equal to u1 plus v1, v2 plus v2, and un plus vn. Okay, so that's the sum of two vectors. And let me give you a quick note here. Okay, so the note says that for okay, as I just said, yeah, for this entry by entry, so we do the sum and even the scalar multiplications that we will see shortly. We do those vectors operations entry by entry on entry by entry basis. Okay, so for this entry by entry addition to be defined, the vectors must have the same number of entries or same dimensions that we will see shortly in a future chapter. They must have the same number of entries. Okay, so good. Let's continue with part 4. Okay. Okay, so this is going to be number 4, and we join some vectors and scalar multiplications. So let's do vector, scalar multiplication. Okay, so the scalar multiplication of the real number r and the vector v is the vector of the multiples. Okay, is the vector of the multiples. You will see shortly what I mean by that. Okay, so let's say we have a vector v. Yeah. Okay, yeah. Why am I changing color anyway? Whose components are v1, v2, vn. So, and okay, and we have r, a real number r, and r. So let's say the scalar multiplication, okay, w, which is equal to r dot v, is going to be equal to r multiplied by our v, which is an entry by entry operation. Vn equals r v1, r v2, r vn. Okay, so that is it. So I'm going to stop here, and in the next video we will do a tutorial about vectors operations. Okay, and yeah, this is very easy, just some entry by entry operations. Okay, see you in the next video. Thank you.